Okay, so in this example, we want to graph the quadratic surface y equals 4x squared plus z squared. So you do have to identify the surface by just looking at the equation, just like you know y equals x squared graphs to be a parabola in the plane, right? You don't have to plug that in your calculator. You know that y equals x squared is a parabola. So you need, with these 6 quadratic surfaces, you need to be able to look at them in standard form, which the standard form, all of the equations I gave you above are in standard form. You need to be able to look at the standard form and say, oh, that's a cone, or oh, that's an ellipsoid, just by looking at the equation. What do you think this guy is? So how do you tell? Well, go back and look at your quadratic surfaces. Which one does this look like, kind of? It kind of looks like number 2, except a couple of things are switched, right? The y and the z are switched. So you can expect this to be a satellite dish-looking object, except its central axis isn't going to be the z-axis. It's going to be which axis? The y-axis. Now, again, if you read the book, it's going to tell you, oh, okay, now you're going to pick a trace parallel with the xy plane, a trace parallel with the yz plane, a trace parallel with the xz plane. Draw the shapes, then connect them. No, don't do that. Just draw the friggin' object, right? And then put in your coordinate axes. So I know what this thing's going to look like ahead of time. It's going to look like a satellite dish on its side. So that's how I'm going to draw it. So it's going to be the same thing I drew earlier. Now the elliptical trace is going to be on its side, though. And then I always draw the parabolic shape in the screen before the other parabolic trace, that is. So let's see, I'll aim for this guy as my origin, vertex. So it's opening sideways. You could put in a horizontal trace, like so. There we go. Then the origin is going to be here. And if I actually want to put in my axes, I can do that. So, okay, z-axis. I'm going to make the x-axis the one coming out. That's the positive x-axis anyway. If I want to go back, I can do that, but I should make it dotted. Okay, and then positive y-axis. The part that's inside the paraboloid, I should make that dotted, so it's easier just to erase. Okay? So x-axis, z-axis, whoops. And that would be the y-axis right there. Now, what if you wanted some details here? What kind of details would you want on this sort of paraboloid? You'd want to know what this point is, what this point is, what this point is, what this point is. And that would depend on where you cut the thing off at. Okay. Now, does the paraboloid stop? Does the paraboloid stop right here? No, it keeps going to the right, doesn't it? And keeps getting wider. So I chose a place to stop it. So that would be at a value of y, right? What value of y, if you wanted to get an equation of this trace, what value of y makes sense to plug in here? So you get nice numbers. So think about a vertical plane parallel to the xz plane, but going through right here, cutting this guy right there, and creating that elliptical trace. What would be a good value for the y that gets you that trace? Well, how about, you could choose 1, but how about 4? So I'm not drawing the vertical plane y equals 1, but I am drawing the result, the cross-section or trace that results when you cut the thing with y equals, I said 1, I meant 4. So the trace that we used here, one of the main traces, is y equals 4. Now, what are the other two traces, by the way? The other two traces are the plane of the screen, which would be the YZ plane. That would be this parabola right here. And so that would be x equals 0. The YZ plane is given by x equals 0. And then this parabola here would be in the XY plane, which would be z equals 0. So implicitly, those are the other two traces I used, the coordinate planes. So the trace for y equals 4 is the only one where it's not the coordinate equals 0. As far as the traces that I've drawn anyway. Okay, so if y equals 4, then the equation that I get is plugging 4 right there. I get 4 equals 4x squared plus z squared. I'm going to turn it around and get x squared plus z squared divided by 4 equals 1. So all I did was divide by 4 and turned it around so that the 1 was on the right side. Does everybody believe that? And now it is in the standard form of the equation of an ellipse. So this would be an ellipse that's in a plane parallel, the plane y equals 4, that's parallel to the xz plane. This guy in purple right here, in other words, is an ellipse that's in a plane parallel, y equals 4 is a plane parallel to the xz plane, isn't it? So how could I figure out what these points are? Well, the center of the thing is at 4, right? In fact, it's 0, 4, 0, if you want to put it in space, right? Because the y-coordinate's 4, and the x and z coordinates are 0. So the center of this ellipse in purple, this elliptical trace, is 0, 4, 0. And then what do you do to graph this thing if you were going to graph it separately? You would go out a distance parallel to say the x-axis. How far would you go? 1. So what would, say, let's just label one of these. What would this point then be? What would the coordinates of that point be? So, yeah, we'd have to be out a distance of 1 there, right? And then we know y is 4, and what's z? 0. And then what would this point up here have to be? Yeah, to go out to this edge of the ellipse, you go out a distance of, is it 4 or 2? You go out a distance of the square root of that number underneath the z squared. So it would be 0, x is 0 at this point, right? 4, 2. Does everybody believe that? And you could get the other points, just take the opposite of the number, of a couple numbers you use. Not the 4, but the other numbers, to get the point in back and the point down here. So be able to come up with those 4 points if you're asked. Does that make sense? Okay.